Atom?
Neutral.
And since that's true, which two columns should match each other?
Electrons and protons.
And so sodium should have how many protons?
11.
How do we determine neutrons? So mass minus proton. So we end up with what number?
12.
What should I fill in for electrons for carbon?
6.
And protons for carbon?
6.
What should I fill in for neutrons for fluorine?
10.
And electrons?
9.
What should I fill in for sulfur's electrons?
16.
And for its mass?
32.
And uranium protons?
92.
And its mass?
38.
And silver, what should I put for electrons?
47.
And for the mass?
107.
Okay, so we have answers on that. We're all comfortable with how we arrived there. Fabulous. Isotopes are not nearly as difficult as most people seem to think they are. So I will give you a short anecdote to see if I can't help explain it. When I was your age, when I was in high school here, I was probably about 100 pounds heavier than what my husband refers to as my fighting weight. So I spent most of my teenage years and the first part of college, heavier than I even am right now, by actually quite a lot. And then I started running half marathons, and dropped to what my husband refers to as my fighting weight or my playing weight. And I remained at my playing weight until this small human being took up residence in my abdomen, in which case I went up about 25 pounds from my fighting weight. Did who I am change? Did my identity change? Did my social security number change? My driver's license number? So the me-ness of me remained the same, regardless of what my mass was. Sometimes it was more massive, sometimes it was less massive, sometimes it was massive in between. Agreed?
Yeah.
Did my behaviors change with change in mass?
Yeah.
How would behaviors change with change in mass?
You're more hungry.
More hungry?
Be grumpier.
Grumpier? How about more lethargic? More sluggish? All these things are true? Didn't change who I am, just changed some of my behaviors. It turns out that elements get their identity from their number of protons, right? And that's always going to remain the same. An element is always an element, is always an element. But atoms of each element can change in their mass. They can have different amounts of mass. When we have an atom of an element, with the same identity, but different mass, we call that an isotope. Now, since its identity remains the same, what subatomic particle must be the same every time? Same number of protons, right? Because protons are where we get our identity. But the mass changes. Hey, on Friday, what did I tell you about the mass of an electron? I had a funny term for it we put in quotation marks. They're virtually massless. So is electron the thing that's changing here? What changes then? If proton stays the same and electron's not the thing that changes, it's the number of neutrons. Now this change in some elements doesn't make a big difference. Behaviors remain relatively the same, it's just one happens to be a little heavier. But sometimes giving something extra neutrons makes it a little bit unpredictable. Unpredictable how? Well, it makes it radioactive. Yeah, kind of a big deal. It makes it what we call unstable. So when you said grumpier with the change in mass, I would occasionally consider grumpier unstable. I'm going to common isotope of one element and then have you work through the isotope of another very common element. What element is this? Hydrogen has 3 isotopes. Hydrogen 1, 2, and 3. So when we write an isotope's abbreviation, its symbol, we always write the element symbol, a dash, and then the mass. So our friend hydrogen 1. Hydrogen occupies box 1 on the periodic table. Box number 1 equals atomic number 1. So what can you tell me about the number of protons hydrogen has? You could hold up the appropriate number of fingers. Is that true for every isotope of hydrogen? How do you know? Protons never change. The identity remains the same. And since we're still talking about atoms, yep.
Oh, when writing the symbol for protons, is that a capital or lowercase?
Lowercase.
Oh.
Electrons, these are atoms. Atoms are always
Neutral.
neutral. So how many electrons do these have?
1.
Number of neutrons. How do you determine neutrons?
Atomic mass minus number of protons.
So if the mass is 1 and there's 1 proton, how many neutrons does it have? And how many neutrons would hydrogen 2 have?
1.
And hydrogen 3?
2.
Only thing that changed is the number of neutrons in its nucleus. One atom happens to be a little heavier than another atom. Only thing that changes there is the mass. Those are different isotopes of hydrogen. They're all naturally occurring, so they are completely normal.
Why would the number of neutrons
Because as it so happens, there are just certain atoms when, in fact, they were created or... I don't like the idea of created, because then you guys think like these things are just like randomly creating. I don't like that. They naturally occur different atoms at different masses. And the reason for their different masses is because they have different numbers of neutrons.
So, what is the 3 then? Is that
The mass number. So it's the mass of that isotope.
Then why isn't there 3 protons, or is it just still?
Still 1 proton, because it's still just hydrogen. So if I were to draw these, the first hydrogen would have just a proton in its nucleus, and then it's like lonely electron out here orbiting, right? The second one would have my proton, and then a neutron, and then the electron out there orbiting. The third one would be 2 neutrons, 1 proton, and my electron out there orbiting. And that's how they naturally occur. We call it natural abundance. There's a way to calculate the masses, but I'm not going to make you guys do that because that'll be another day. Actually, another year, called next year. Carbon also occurs in 3 naturally occurring isotopes. Go ahead and figure out protons, neutrons, and electrons for carbon with your partner. Ready, set, go.